The next differentiation rule we're going to look at is what's called the power rule. And while we won't derive it completely, we'll at least get a little evidence on how to derive it. And most textbooks have a derivation of the general form. But let's say I wanted to take the derivative of x. Let's start with x to the 1. Well, the derivative of x to the 1, we'll use the limit definition. Limit as t approaches x. My function is this one, f of x equal x. So it's going to be f of t minus f of x over t minus x. So we're going to do this for just a few cases to show how it works. Well, f of t is, so its limit as t goes to x. F of t is t, replacing x by t. F of x is x over t minus x. Well, that's pretty nice. That cancels out immediately, and you get the limit as t approaches x, canceled out to be 1. The limit of a constant is 1. Okay, so we can see what we're shooting for, but let's get a few and then recognize the pattern on our own. If I do x squared, it's going to be the limit as t approaches x. F of t is t squared. F of x is x squared divided by t minus x. This will factor as a difference of squares, so I'll have the limit as t approaches x, t minus x, t plus x, divided by t minus x. And those t minus x cancels, leaving me with the limit as t approaches x of t plus x. And since I no longer have a denominator, all I have to do now is just turn my t's into x's. And there it is. That's going to give me x plus x, or 2x. Let's do one more. If I do the cubes, I get the limit as t approaches x. F of t is t cubed. F of x is x cubed over t minus x. That's going to be the limit as t approaches x. Again, this will factor. It's a difference of cubes. It's t minus x times t squared, tx, x squared. But the main point here is the fact that this t minus x shows up again. So I get the limit as t approaches x, t squared, tx plus x squared. And at this point, I can turn the t's into x's. I get an x squared here, an x times x here, which is x squared, and an x squared. I get 3 x squareds. You can see the pattern of what's going to happen. If I did t to the 4th minus x to the 4th, that factors. Any difference of powers will factor, whether it's squares, cubes, fourths, fifths, whatever. It turns out you can always factor a t minus x out of that. And there's a general formula for that I won't get into. And then once you turn your t's into x's, you're going to get something of this form. That when you take the derivative of x to a power, you take the power out in front and reduce the power by 1. Now, I did this for some integers, and I just talked about doing it for integers, but what I've got written here is that'll hold for any real number. Now, that's usually not proven in textbooks until later that it holds for any real number, but I'm just going to go ahead and give it to you now, just because we're going to use it when we need it. If you want to look it up in a textbook once it comes up, then certainly you can see the general proof. But so that's saying it, that I can take that for integers, for negative numbers, for radicals, and so forth. So let's take a look at some examples. So I got about 6 of them down here. All right, so here I've got y equal x to the 10th, and I want to find y prime. Well, according to the power rule, y prime, you take the exponent out in front, and you reduce the exponent by 1. Now, you don't have to put the full step in there of showing this reduction. You can just write 10x to the 9th. So, very nice compared to having to go through the entire limit process, trying to somehow factor a t to the 10th minus x to the 10th. We can go straight to this power rule. So, only use the limit definition to find a derivative if you're specifically told to do so. We're going to have rules for all our basic functions, so there's no reason to go through the limit definition. Here's another one. Derivative of t to the minus 2. I said this works not just for integers, but even for negative integers. Not just for positive, but even negative. So this is going to be negative 2, t, derivative's t, so I use this notation, ddt. This is going to be minus 2, minus 1. You bring the exponent out in front, and then reduce it by 1. So in this case, I'm going to get minus 2 t to the minus 3. Typically we don't leave negative exponents in our answer, but since this started with a negative exponent, I'm going to leave it. Well, actually I'm not. If you didn't want to leave it, which I don't, you could write it like that. Okay, number 3, the derivative with respect to x of pi to the 100. Now, you see an exponent there, just jump in and start using the power rule. Recognize that pi to 100 is a constant, so this actually goes from the constant rule, that's 0. So don't, it's a little tricky to try to fool you like that, but anyway, just make sure you know what you're taking the derivative of. Alright, here we've got the derivative of square root of x. What I'm going to do is rewrite that as the derivative. I got to get a power on this, but we know that a square root is a 1/2 power. And so now I can use the power rule. Take the exponent out in front and reduce the exponent by 1. That becomes 1/2 x to the minus 1/2 when you subtract. And as I said before, I usually want to get rid of the negative exponent, so that's going to become 1. And so that's going to go down to the denominator, and I've already got a 2 in the denominator, so it's going to take a 1/2 with it. And I'll go back to the square root notation. This is 1/2 square root of x. That's one that's worth memorizing. If you want to make a list of things to memorize, I mean, certainly the derivative of a constant is 0. That's one of our rules. But the derivative and the power rule certainly is worth memorizing, but this is a particular power rule that shows up in enough simple examples that you probably just want to have it memorized so you don't have to redo this every single time. The derivative square root of x is 1/2 square root of x. So the tangent line slopes on that square root graph are given by this formula. The slopes of the tangent lines are 1/2 square root of x. Nothing inherent that I can see there, but that's just an easy formula to remember. Derivative square root of x is 1/2 square root of x. This is going to be another one you'll want to memorize. What I'll do here, you got to be careful that you don't try to make up a quotient rule here. Don't say that the derivative 1/x is the derivative of 1 over the derivative of x. I mean, there's some intuitive thinking there, but this is going to give you 0 over, we did the derivative of x above, you get 1. This is wrong. Well, this one's wrong. We don't have a nice quotient rule. So with limits, remember, we did have a nice limit quotient rule. You just take the limit at the top and limit at the bottom as long as both of those limits exist. But unfortunately, that doesn't work for quotients, for derivatives of quotients. So what I have to do here is first rewrite it as the derivative. Well, I just need a power. Now I can do it. Once I get it out of the denominator and I'm looking at just x to a power, then I get -1 x to the -1 minus 1. That's what the rule said to do. But that's going to be minus x to the -2. And since I didn't start with a negative exponent, I'm going to go ahead and put that in the denominator, and my answer is -1/x squared. This is another one that's worth memorizing. It just shows up enough. The derivative 1/x is -1/x squared. Derivative square root of x, 1/2 square root of x. Derivative 1/x, -1/x squared. And then the rest of them you work out. I mean, you can memorize whatever you want, but it's not worth memorizing x to the square root of 2, for example, because that's easy enough to work out. That's going to be square root of 2, x to the square root of 2 minus 1. And I really can't simplify that in any way. And as I said, most textbooks don't allow these kind of exponents for a while, but eventually they say, okay, yeah, this power rule works for any kind of power. So I'm just going to start using it for any kind of power. So that's our second rule. So we've got a constant rule, and now we've got a power rule. So certainly you want to remember that power rule. And note that it does work for derivative of x, because that's derivative of x to the 1. You get a 1 times x to the 1 minus 1, which is x to the 0. So it does just give you that constant 1, which is what we derived above when we did it with the limit definition. So the derivative of any linear term gives you, of just x, it gives you just that x. And it gives you 1, the slope of that line. But we'll get some more rules. And to where, as I said, eventually we'll be able to take the derivative of any of our basic functions that we can write down.